So, before we get into today's example problems, I would first listen your doubts. If you have any doubts from the previous lectures or previous assignment problems, you can ask me now. Maybe I will wait for 5 minutes. I hope I'm audible. Can someone confirm it?
Yes, sir.
Okay, thank you, Digant. Oh, Yokesh, actually, I posted it in the YouTube. Um, so if you go to the portal, the Rocket Propulsion NPTEL portal, there will be one section called problem solving session. And if you click that, it will open a new, it will open a Excel Google Sheets. There you can get the YouTube links. So maybe I can share it now also, no problem. So I updated a little late, so you may not be able to see it maybe 2 days back. So I updated yesterday, I guess. I will share the playlist. What you could do is I will upload the 12-week YouTube links everywhere in that playlist only. So as soon as each and every session ends, you can view that playlist for recordings. Okay. So this is my playlist. I hope you attended the other tutors session, right? I hope you attended other tutor sessions. It's on Monday, Mondays 7 to 9, or I'm not sure. It's on Mondays. He will upload a separate YouTube link also, so you can check that also. Okay. Yes, Tigan, you can unmute.
Sir, there is a question in assignment one in which there is a different answer in solution and different answer in the answer that we have wrote.
I see. What was the question?
Sir, fifth question of assignment one.
Let me open it. Give me a minute. Questions, right?
Yes, sir.
Week one, which question?
Sir, fifth.
Fifth.
Assignment one, fifth question.
Okay. The change in momentum of stone while rebounding the stationary surface. Is that the question you have a problem?
Yes, sir.
So what was the problem?
Sir, actually we wrote 4,000, but when we saw answer, the accepted answer was minus 4,000. And
I see.
in solution, the answer is given 4,000.
Oh, I see. Let me check once. So basically, you are asked to get the change in momentum, right?
Yes, sir.
Okay. So when you say change in momentum, uh, there is a difference in velocity. So final minus initial, right? Final would be minus 1000 plus minus 1000. Shouldn't it be minus 4000? Maybe I will. You share your view. Okay.
Okay,
I
sir.
will just write it. Somewhere here. 1 second. So sometimes answer key might be wrong, or sometimes the solution also might be wrong. Let's see what we get.
Okay, sir.
Where is that question? So it is telling that there is a stone. which travels at 1000 meters per second, right? So
Yes,
there
sir.
is this some stone is there. It is traveling at 1000 meters per second, right? And there is this stationary wall. Okay. Is the mass of stone given? Yeah, it is given to be 2 kg, right?
Yes, sir.
So you are asked to find the change in momentum. I hope you can see my screen. Yeah. So you are asked to find the change in momentum, which is m times delta v. It's nothing but m times vf, or let's not write it like this. So p final minus p initial, right?
Yes, sir.
Which is m into v final minus m into v initial, right? Which is equal to m into v final minus v initial, right? So now what we know is v initial is 1000 meters per second, and
Yes,
it
sir.
has been told that it is going to reflect back normally,
Yes.
right?
Yes.
So so it is the reflecting, since it's a normally, and is reflected without any change in velocity. So without any change in velocity, it gets reflected, which means it is going to be reflected in this direction, right? So
Yes,
if
sir.
we consider the x to be like this, x and y, this is going to be minus 1000 meters per second, right? So this is going to be minus 1000 meters per second. So if you substitute here minus 1000 minus 1000, which is going to be minus 4000, right?
Yes, sir.
So this is the answer. Sometimes solution they didn't consider this direction, I guess. So, but this is the answer. So, is it clear? Uh,
Yes, sir.
okay.
Thank you, sir.
Yeah, sure.
Sir, I had a question. Due to my college exams, I couldn't complete assignment one and two. So, will it be affecting like the program as such?
It depends on, if you are, let's say, appearing for the exam, you are supposed to get some certain marks to be considered as a pass, right?
Yes, sir.
So, in that way, it affects. Um, yeah, so it will affect, but not that much. So, how much you need to get a pass mark? So, there's some certification criteria, right?
Yes, sir.
So, based on that only, you will be graded. If you leave one or two assignments, I don't think so. It is going to mean like you won't be able to attend the exam and you won't be able to get the certificate. It just means that it affects your grade. That's all in the exam.
Okay.
Other than
Okay, sir.
that, nothing's going to happen. Um,
Oh, thank you, sir.
I think so. I think so. You no need to. Uh,
I'll complete it in this week. Just that I wanted to confirm.
no problem. It's just your grade might get affected. Uh,
Okay.
but let's see, if there are 12 assignments and if you're able to complete 10 fully, I think it will be some 80%. And if you're able to get good marks in exam, I think you can easily cross 80%,
Okay. Yes,
80%
sir.
or
Thank you.
70%. No problem.
Excuse me, sir.
Yes, Vaishnavi.
Sir, once I have registered means how many times I can attend this program?
Understand. So, if you have registered this time for exam also, you can give exam this time and you can get a certificate. If you want to do, I think this course might be offered 1 year later. So maybe next year they might offer the course. So at that time again you can register and take the course. You have no restriction on that.
Okay, sir. Okay. Thank you, sir.
Do anyone have any more doubts in the assignment problems?
Sir,
Yes, Tigant.
as you told us in fifth question, Sir, what if we changed our frame of reference, sir? We took initial as a minus 1000 and final as a plus 1000.
Okay. So uh, the so okay, let's have a different frame of reference. No problem. So what it has been given is velocity is 1000 meters per second. Okay. So this is not going to change. Initial velocity is going to 1000 meters per second. Whether the stone is coming and hitting this side, let's say this is your x. Okay. Is that what you are asking? Let's say I have something like this. See,
Yes,
the
sir.
the question is given as 1000 meters per second, which means that whichever direction you take along that direction, along the positive direction, there's going to be 1000 meters per second. The velocity is going to be 1000 meters per second, right? So even if you take this to be this as your reference, okay? So even if you take this as your reference, what happens? Stone is going to travel in this direction because velocity is given to be positive, which means it should travel in the positive x direction, right? Then
Yes.
maybe if you solve for this, what happens? It is again going to be m into vf minus vi. Again it is going to be 2 into minus 1000 minus 1000. Again it is going to be minus 4000. It doesn't matter which frame of reference you are trying to take. It is based on what is your initial velocity of the stone. If the initial velocity of the stone is positive and the final velocity is negative, then always you should find momentum from final minus initial, right? And whenever you do it, for whichever frame of reference you take, if your change in momentum is going to be negative.
Okay, sir. Thank you, sir.
Is that clear?
Yes, sir.
Okay. 1 second. I think I got disconnected. If we have no more questions, maybe I will start with today's question. Okay. So today we are going to solve only one problem. We are not going to solve so many problems. But with this one problem, you should be able to solve all your week 3 assignment problems. And this is also going to be interesting. I'm going to show a nice fact after you perform this exercise. Uh, I named it as design of rockets, just to cover like it's just for fun. I made it as design of rockets. Anyway, uh, what we will do today is we will solve this one problem. Okay. What we will try to design a three-stage rocket motor. Okay. And we will be using the three-stage rocket. It's not rocket motor. It's rocket. Using this three-stage rocket, we will launch payload. Payload can be anything like satellite. This satellite of mass 500 kg and altitude of 500 kilometers. So we need to launch a satellite of 500 kg, and we should station it at 500-kilometer altitude above the Earth's surface. Okay. So what are the other things given in this mission? Is the state of art structural mass ratio available can be taken as zero point 0.1. So uh, what is structural mass ratio? Can anyone guess what is structural mass ratio? It's fine. You can give any answer. There is something called structural mass ratio.
Hello, sir.
Yes, Mohammed.
Yeah, structural mass can be defined as structural mass divided by total mass of the rocket.
Exactly. So, what is the convention we follow for that?
Alpha.
Is it alpha or beta?
Uh, I think just a
Beta.
minute, sir. Beta, sir. Sorry.
Okay. So, uh, is this fine? Can I write like this? We can take at ms to be mass of structure and m not to be initial mass of the rocket or at
Yes,
any
sir.
stage. Okay.
Yes.
Okay, so this we are going to be this we are going to take as point one. So this is something comes from design perspective. So this is something we can't have a control over as a propulsion engineer or it's a aspect of structural engineer. How well he can design a rocket motor or rocket with a structural with very less structural mass ratio. Do we need less structural mass ratio or more structural mass ratio? What do you think? So what this beta signifies? So what it tells is the structural mass is zero point 0.1 times the overall mass, like the total mass, which is 10% of your rocket mass is going to be just the structure. And what happens to the structure after launch? Maybe after payload separation.
It will not. It will be like once payload separated, it will come to sea, or otherwise it will be useless.
Right.
Right?
It is actually useless. After the payload is separated, it's just dead weight. It is of no use.
Yes.
It just holds the propellant and the payload together. And after payload is separated, after mission is accomplished, this structure is it's just a dead weight. It's not going to contribute in any propulsion aspect. So, as a design engineer, what people will try to do is they will try to reduce this dead weight as low as possible in a rocket because the if a rocket, let's say the total mass is 100 tons, and if the structural weight is some 10 tons, um, if you can reduce the 10 tons to 5 tons, then you can raise the 5 tons of payload mass or some amount of payload mass, right? So you can, with the same rocket, you can send a higher payload. Okay, so that is the reason they will try to reduce, or it comes from the design aspect. For now, let's take a state of art mass ratio to be zero point 0.1. It is been that is what it's presently. In fact, if you take a solid propellant motor, rocket motor, it's going to be around 0.08, and liquid propellant rocket motor is going to be around 0.05. Some very well designed rocket motor is going to have even 0.03. So there are different ways of it directly comes from the design aspect. So let's not worry more about this. We'll just assume it to be zero point 0.1. Okay, for every stage. Well, if we have three stages, it's going to be zero point 0.1 for every stage. Okay, and then what else we have is the mass reflex velocity from the rocket at any stage is given to be 2000 meters per second, which is nothing but velocity of jet, right? This is what we usually follow, velocity of jet to be 2000 meters per second. So at any stage, which means like we are using the same kind of propellant, okay, um, inside every stage, and we are going to burn it, and it is going to give me uh, and we are going to use same nozzle. You haven't studied nozzle, it's in week 4, I guess. Anyway, at the exhaust we are going to have 2000 meters per second at every stage. Okay, so these are the given inputs, and these are all coming from the design aspects of different discipline. Okay, so the our mission requirement is to launch a 500 kg payload at an altitude of 500 kilometer, and the maximum design the engineers can give is mass ratio to be zero point 0.1, and the propulsion engineer will tell I have only this propellant with 2000 meters per second. So with this information, you have to design a mission. We have to design what are the three stages of rocket motor, what is the let's say amount of propellant and amount of what is the mass of propellant at each and every stage, what is total force given by each and every stage, and finally how many it should be the primary mission requirement, what should be the delta V for this. So to place a 500 kg of mass at 500 kilometer altitude, what is the delta V requirement we need, right? So all these things you have to find out, and you have to design these three stages. Okay, so that is what I divided as a five uh, questions here, um, which should be useful for your week 3 assignments, and also in general how to design a stages in rocket. Okay, so let's get started. Initially, what we should first find is what is the velocity requirement, velocity increment. So in order to keep a mass of in order to keep a uh, mass at a certain altitude in the atmosphere, what is the velocity increment unit? So in rocket science, we always try to see it as a velocity increment rather than what you say, the amount of distance traveled, or like, so how do I put this? Let's say you are going by a car, okay, and if you want to tell that I want to reach this place from here. So what is the mission? So the mission is to attain certain distance, right? But in case of in certain distance at a certain period of time, right? Rockets is just the mission is to attain certain velocity at the orbit, because to be in the orbit we should have some velocity, and the orbital velocity, and the I have zero velocity, I need to reach that altitude and I need to have the velocity. That's why we always deal with delta V. So for here, what is the ideal delta V we need? That is my first question. How do we calculate this? This you guys should be familiar with, because you already solved week 2 assignments, right? What should be the ideal velocity increment required for the mission? How do I calculate it? Is this clear till now what I am trying to convey?
Yes,
Yes,
sir.
sir.
So how do we calculate delta V? Or let's say, what is the total velocity increment you need? How do I calculate it? So you understand the fact that we need velocity increment, right? Because satellite, it is at ground, it is going to be zero velocity. It's going. So if I want to put it in the orbit, it cannot be at rest in the orbit, right? It should have some velocity so that it goes round and round in the orbit, right? What should be the velocity? That is what we need to find out. We find out. So are you? Uh, do you know any formulas that we derived previously to find out? Maybe the um, concepts behind on deriving those formulas.
So Vg multiplication of ln mi and divided by mf.
Okay, the delta V is equal to Vj ln of I by mf, right?
Yes, sir.
Okay, so but uh, this is the delta V given by the rocket. I'm not asking whether the delta V. I don't know the mi. I don't know mf. I didn't give anything about the rocket. Mi
Yes,
and
sir.
mf you are going to find out, right? How
Yes,
is
sir.
this going to help you in finding the delta V? So there is two things. This is also delta V. This is also delta V. See, these two are delta V's only, but this is the delta V given by rocket. So if a rocket gives you a delta V, you should know what is the delta V you need in order to design a rocket. So this equation won't help, right? So if I know the rocket, I can find the delta V given by that rocket. I'm going to design the rocket. For that, I need to tell what is the delta V, so that I will design a rocket such that it gives me the delta V, right? So basically, I'm telling that I want to put a mass of this at 500 kilometer altitude. What should be my delta t, delta v? So let me write it down. Maybe you can recall it. Delta v is actually g me by re times e plus 2h divided by re plus h. Can you guys remember this formula? So you may be referring it to be VT or something, is it?
Yes, sir. Yes, sir. VT.
So
Total
what this
velocity.
VT means? The total velocity increment, right?
Yes, sir. VT.
So what this actually tells is, from where this concept comes is, this is required for the mission. There are two things. This is required for the mission in order to put a payload on the orbit. So in order to put a payload on the orbit, what is the delta V? And what is the velocity increment I need for that payload? That is this formula tells us that. And as soon as you know the velocity, the total velocity increment you need, you can design your rocket such that it gives you that increment to the payload. Okay, so this is required for the mission, and the delta V, this is going to be, it is the rocket, it is how much delta V the rocket is going to give you. Okay, so that is the difference between these two. This, if you remember, it's going to be addition of potential energy and kinetic energy, right? So when the payload is at surface of the earth or something, it is going to be have, let's say, zero potential energy and zero kinetic energy, right? And if it is at the orbit, you have raised its potential energy from 0 to 500 kilometers, and the kinetic energy has raised from 0 to orbital velocity, right? Then only you can put it in the orbit. So this total change in energy you are measuring in terms of VT, total velocity required for the total velocity increment. That is your mission requirement. So in order to achieve this delta, you are going to use a three-stage rocket. So is the concept clear? So do you have any doubts? What is the implication of these two formulas? Both tells about delta V. So here Vt is nothing but total velocity increment, which is also a delta V. Is this fine?
Yes, sir.
Did I confuse? It's fine, right? So if this is fine, maybe you can substitute the uh, values, and you can let me know what is the uh, delta V required for this mission. So I just want to connect whatever you learned in the previous week to this week. How these two equations are related to each other. That's why I made this small exercise before starting the calculations of staging in rockets. So it should be placed at 500 kilometers, right? Then what should be the total velocity increment I need? Could anyone please tell? Are you guys calculating or? I hope you can understand. So we have 10 people here, oh, including.
Sir, 8.18 kilometer per second. I think so.
So it is 8.18 kilometers per second. Right. All right. So in order to put a satellite, okay, uh, in order to put a satellite of 500 kg at the orbit of 500 kilometer altitude, you need a delta V increment of 8.18 kilometers per second. Now, this delta V increment should be given by the rocket, okay, and that rocket is should be able to produce enough thrust to give me this delta V increment, okay. So, in order to have this much thrust, we are going to divide this rocket into three stages, and we are going to perform some calculations that how many stages of all the three stages, what is the mass of these stages. Um, should be in order to how much mass of propellant you need uh, to achieve this delta V is not we are going to see going forward. So the next question is, so if anyone has any more doubts, please ask me now. I mean, you can ask me, you can stop me anytime and you can ask me, okay. So what we know till now is we know that delta V to be 8.18 kilometers per second, okay. So this is done. Now what we need to do is we were asked to tabulate propellant mass, structural mass and payload mass for every stage, okay. And what I know is mass of payload is 500 kg, which is at the top of third stage, right? It is not at the first stage. And what else I know that beta to be zero point 0.1, which is for all the stages. Let's say beta 1 is also 0.1, beta 2 is also, and beta 3 is also zero point 0.1, okay. Which is nothing but mass of structure by mass of 0 I, I in the sense like whichever stage it is. I varies from 1, okay. Now how do we go forward? We start our calculations. Can anyone give me an hints or something? And we also have Vj to be 2000 meters per second. So in order to do this, we need to use this equation, right? Mi by mf. Okay, what we know is we know delta V, we know Vj, but we don't know mi and mf, right? And one more thing is this is for a single stage, right? So what about multi stages? We have three stages, right? For multi stage rockets, how do you perform this calculation?
So we need to add each and every stage of delta V, sir.
Wonderful. So the total delta V total is going to be delta V1 plus delta V2 plus delta V3. So for each and every stage we are going to have Vj, and we are going to assume Vj to be constant, which means the propellant is going to be same, and yeah, we are going to assume Vj to be constant. If you do that, what happens? First stage ln of mi by mf of second stage, mi by mf of third stage, right? But still, yeah, this is fine. Delta Vt, this is going to be for three stage rocket. Okay. So yeah, we are asked to assume velocity increment is equally divided by the stage is also there, which means that We'll come later, no problem. Now here, this total velocity increment we know, Vj we know, right? Uh, so, but still this equation doesn't help us. We don't know Mi and Mf, right? Of each and every stage, we don't know that, right? How do we go forward with this? Can anyone guess what could be the uh, way to go forward in order to find all the masses? Okay, so one more thing. Uh, Maybe you can see via this. Do we know initial mass at the first stage? Maybe I'm going to ask a series of questions. By that way, you can find a way to solve this problem. Okay. So, do you know Mi or Mf at the first stage with the given data? It's fine. Even if you give wrong answers, it's fine. Uh, Need to understand few certain concepts in order to solve this problem. It's just you can substitute in equations and you can solve the problem and you can give the answers, but the physical significance is important, right? So, do we know Mi and Mf at the first stage? So that is what we need to find, right? And Mf we need to find, right? Okay, Yokesh is telling, but they give useful mass, which is 500, which
Yeah,
is
sir, that
payload
is
mass.
the payload mass only.
Okay, so where does it fit here? So
So
what we know. Uh-huh.
basically the payload mass will be same for all three stages.
Okay, there is one statement. Okay, payload mass is same for all three stages. Okay, let me ask other one. Is this right? Do anyone have different answers for this? Do everyone agree with this? It's just small set of people. You can freely talk.
Yes, sir.
Okay, you are also thinking payload mass is same for all stages. Okay. Who else? Ahmed, Sandra, you. Yes, Mohammed.
Yes, sir.
Okay. Okay. So
Actually, in each every stage, plus structure, right? Including three stages, considering those three stages only, it will be final payload will be like 500, right? In each and every stage, it should not be 500.
actually, you
In
are
my
breaking. You're breaking, Mohammed. I couldn't fully get your answer. So you are telling
This
that.
is
Yeah, yeah.
actually yes, sir. Then it is. Not like it could be our final payload will be like 500. It will not be like in each and every stage. In each and every stage, payload will not be like 500 kg.
Okay, you are telling
So
no,
considering
right?
those stages, three stages only, 500 will be like.
So So you're telling yes or no? So Muhammad is telling third stage payload is going to be 500. That is true. How about second and first stage?
It will be 500 only, sir, because it is not going to change its weight. Only the yeah, after the first stage has burnt, it will be released into the orbit. So the weight of the rocket, total weight of the rocket is going to be less. Not the payload weight is not going to less anyway, because it is going to be like ejected in the orbit in the last stage only. Still, the last stage the payload has the same weight.
Right. So you need to note that payload mass is 500 kg. That is true, but the final mass of each and every stage is going to be different. Right. So okay, I agree with you. Payload mass is going to be same. Um, Let me put it in this way. So payload mass in the sense just the payload. Okay. So let me ask another question. What is my MF at all at each and every stage?
So we can do one thing. So MF of first stage will be MF.
Okay.
Then second stage is MF. We can take as a total mass, final mass as a MF. Then for second stage we can do MF minus M1, which is the mass of first stage, total mass of first stage. Then for third stage we can take MF minus M1 minus M2, which is the mass of first stage and second stage.
Okay. Let me go in this manner. Let's write it from third stage. Okay. What should be the my final mass at the third stage?
So total mass of the rocket, that is Mi minus initial mass of the rocket, Mi minus
Mi minus
minus MF2
okay
minus MF1.
minus m of okay okay. This is also yeah, but you are thinking in a very complicated way. It's so simple. At the third stage, what I'm going to have is the propellant is going to be depleted, and I'm going to I'm going to um, uh, stage, right? I'm going to get separated from the third stage, and what else is remaining is just payload, right? It's just
Yes,
500
sir.
kg, right?
Yes, sir.
Okay, so whatever you said is also right, but it is little bit different. So let's say what is mi? Mi is going to be m of 1 plus m of 2 plus m of payload, right? And then we have minus m of 2 and minus m of 1. Whatever you said is right. These are all going to get cancelled, and finally m of payload is going to be there, right? So whatever you said is also right, but you can think in very simpler terms also. The third stage final mass is going to be 500 grams, 500 kgs. So in this equation, what we know is only this mf at final stage, right? What we don't know is we don't know this 1, 2, 3, 4, 5. We don't know 5. Like there are 5 unknowns, right? So and we have only one equation. Will we be able to solve it? So is this clear? We know only payload, which is the nothing but third stage, right? We should start solving our problem from where we know. Okay, so we know the third stage final mass. Now we should try to find the third stage initial mass. Okay, so how do we find the third stage's initial mass? So what we told is there is one more statement in this question. It is telling that assume velocity increment is equally divided by the stages. So what we wrote was delta Vt is nothing but delta V1 plus delta V2 plus delta V3, right? So I'm going to assume one more thing, which is nothing but delta V1 equal to delta V2 equal to delta V3 is equal to delta V. Then what happens to the equation? Delta Vt is going to be 3 times delta V, right? So each stage is going to give me same delta V's. That is what this statement is telling us. So what we can get is, we know that delta V of any stage, let's say I, okay, it's nothing but delta Vt divided by 3, because we have 3 stages, okay. So why do we need to know this? Because what we know is delta Va of, let's say, third stage, it's nothing but Vj ln of Mi of third stage divided by Mf of third stage, right? Here we know Mf of third stage, we know Vj, and if we know delta V3, we can find the initial mass of third stage, right? And then one by one we can go forward for the subsequent stages. That is the reason we start from where we know, okay. So can anyone tell what is delta Vi, which is, it's nothing but 8.18 divided by 3, right? How much is that?
2.72, sir.
Okay, 2.72 kilometers
Hey,
per second, right?
hey, yes, sir.
Okay, very good. So then can anyone tell me what is Mi3, which is nothing but exponential of delta V3 by Vj, and mf3, right, times mf3, which is nothing but payload. So how much is this mi3, initial mass of the uh, third stage? Can someone quickly calculate? So Vj is going to be 2000 kilometers per second, so 2000 meters per second. How much is it coming to be? By the way, this is clear, right? What we are doing, we need to find the mass of propellant at each stages. That is our aim, right? Well, we need to know how many propellants I need to load in each and every stages uh, in order to achieve, in order to put a payload into orbit. That is our mission. Is it coming to 2.72 divided by 2 exponential of this into 500, right? How much is this? So I'm getting some 1948 kgs. Is this right?
Yes, sir.
Okay, so we got something, mi3 we got. So this is the initial mass of uh, the third stage. How do we find the propellant mass? What is it comprises of? Initial mass of third stage is going to have some payload, which is 500 grams, plus some uh, mass of structure, plus some plus mass of propellant, right? What we know is payload is 500 kgs and mass of structure we don't know. But what we know is and mass of propellant also we don't know, right? And this is now 1948 kgs. What we know about mass of structure? Mass of structure at third stage divided by mass of I at third stage is going to be beta, which is going to be 1.1, right? We know this, so we can substitute it here. We can write for third stages, okay. So 1948 equal to 500 plus 1948 times zero point 0.1, right? Plus mass of propellant. How much is mass of propellant? It's just quick calculations. Can someone tell? I'm assuming that you are following me.
Sir, it's coming out 1253.2.
Okay, 1253.2 kgs. So we see that the propellant at third stage is going to be 1253.2 kgs, right? All right. So what we do here is now we know. Now let's go to second stage. Okay, this is what we did was is for third stage. Are you talking? I couldn't hear you. Do you have any questions?
Yes, sir, yes, sir, I'm actually watching, sir.
Okay, so do
That's
you have
fine.
any
That's fine,
questions?
sir.
It's fine. Okay, okay, fine.
Right on, boss.
Okay.
Thank you.
And then now we have second stage. Okay. How do we calculate for second stage? So actually, what we did was we did a small mistake here. Can anyone identify? Can anyone tell something about MO3? Is this 500 kg? So what I told was the final stage of third is just going to be payload, right? What we didn't consider is there's going to be a structural mass, right?
Yes, sir.
Should shouldn't there be structural mass? There should be structural mass, right? Once the propellant is over, there's this structural mass also, right? Uh,
Yes, sir.
Later only we try to remove it. Okay. Uh,
Yes, sir.
the at finally we have structural mass also. So and what we know about this? This is going to be 500 plus structural mass is going to be zero point 0.1 times mi of 3,
Yes.
right? So now if we put these things into here, we will get instead of m of 3 we will write 500 times 500 plus zero point 0.1 times mi of 3, right? And then if we do this calculation, how much are you getting? So let's say exponential of delta v3. How much is delta v3 by vj? Exponential of delta v3 by vj is going to be 3.896 times 500 plus zero point 0.1 times mi3, right? Which is equal to mi3. And what we can do is we can take this on the other side, rearrange all these things, and uh, how much are we getting? Maybe I will do few more steps so that you can understand. So this is going to be 1948 plus 0.3896 mi of 3, right? And mi of 3, this can go this side, so it can be um,
Sir, it's 3191.349.
okay, very good. I have an answer. 31,
91.
okay, 3191, okay, 3191,
349.
okay, point 0.3, okay, 35 kgs. Anyway, we are dealing with some thousands of kgs, so we can ignore after points, after decimal places. It's fine. We have mi of 3, so from there we can find which is nothing but mass of, as I said, it's going to be payload plus mass of structure at 3 plus mass of uh, what would be propellant at 3, right? So then if we perform this calculation, what would happen? It would be zero point 0.1 times 3191.35. This is going to be 3191.35 plus mass of propellant. What would be mass of propellant? Plus 500.
Sir,
Two three
it's
seven two sir. Point two.
Okay, 2372
Point two
kgs. Yeah, zero point 0.2
kgs.
kgs. Okay, now this is our mass of propellant, and what we also know is mi at 3, which is also 3191 kgs. And let's, for the sake of completion, we will write ms at 3 also, which is going to be 319.135, right? Right. So these are the,
Sir,
yes.
sir, can you show me the calculations of MF3 one time?
Okay, so is this one?
Yes, sir.
So you understood, or
Can you repeat it one time,
yeah,
sir?
yeah. So at the end of final stage, okay, all the propellant is burnt out, right? But structure remains there, right? Structure and the payload is going to be there at the third stage, right? What we know is, in that final mass, we know only payload. Since we know payload in that final mass, we start our calculation from there. Okay. For other stages, we don't know anything about structure or payload, or uh, like the initial mass. We don't know anything. So that's why we start from here, and we know that at the end of final stage, let's say if you look at this rocket, um, we have this satellite which is 500 kg, right? And we also have this structure around it, which is also some zero point 0.1 times initial mass of 3, right? So this whole thing, okay. So this is payload, and this is the third stage, and the end of third stage, the propellant here will get depleted, but this structure is going to be there with the payload, which is satellite, okay. So this is going to be 500 kgs, and this is going to be some zero point 0.1 times r, nothing but beta times mi of 3, okay. So that's why we wrote the final is going to be 500 kg plus structure, which is ms of 3, which is nothing but beta times mi of 3. Is that clear, Yogesh?
Yes, sir. Now it's clear.
So there's going to be structure also at the end of every stage, so that's what you need to take into account, okay. That's the takeaway here. So now, coming to the second stage, again what we need to know is mf at second stage and mi at second stage, right? Then maybe if we write, let's say delta v2 is going to be vj times ln of mi of 2 divided by m of 2. The equation can give us mi of 2, but what we need to know for this is m of 2. So what should be the m of 2? So at the end of, again let's think logically, okay, at the end of second stage, what is left after all the propellant is gone? What is left? The end of second stage, this whole propellant is gone, right? We have this full third stage is going to be there, and we are going to have this satellite, which is payload, right? But you should understand, for the second stage, this whole thing is a payload, because third stage is not ignited. It is just stays there as a as a mass, and in addition we have a satellite. So these both, the both is considered to be as a one single payload for the second stage. So for the second stage, third stage and payload, or third stage and satellite is called as payload. Okay. So if that is the case, what we are going to have here is this mass of satellite plus mass of third stage, but we can write these two together as mass of third stage, right? Or maybe mi of 3, right? And in addition, what we'll have, we will have structure of second stage. Is this right? Do you guys agree?
Yes, sir.
Right.
Yes, sir.
Okay. So for the third stage, so third stage is just being idle till the second stage has been second stage is completed. Okay. So that's why it is also considered as a mass, as a payload for the, or useful mass in our sense, a useful mass for the second stage. Okay. And we also have a dead weight or structural mass at the second stage, at the end of everything. Okay. Now then this would be mi of 3 plus ms of 2 plus m of propellant at second stage, right? This would be mi of 2. But anyway, we will calculate mi from here. So what would be delta v? Again, we have 2.72 and then 2 ln of mi of 2, which we will keep it like this, and then divided by m of 2 is nothing but mi of 3 plus ms of 2. What we know about ms of 2, which is going to be uh, 0.1 times mi of 2, right? Isn't it? So because we assume that structural mass ratio is going to be 0.1 everywhere. Okay. Now if we try to solve this, what will happen? We will have mi of 2 is equal to exponential of 2.72 divided by 2 times mi of 3 plus zero point 0.1 times mi of 2, right? What we know is, we know this thing, and we know mi of 3, which we recently found, which is 3191.35, 3191.35 plus zero point 0.1 times mi of 2. We'll keep it like that. This side is also mi of 2. So if we try to solve, how much you are getting mi of 2? This turns out to be 3896. How much are you getting? Getting 20,370. Is that right? Come on, do you guys have calculator with you? It should be easy, right?
Yes, sir, correct. Same mass are getting.
Yes, sir. Same.
Thank you. Uh, and so similarly, can you guys tell me what is the propellant and structural mass? Propellant and structural mass. Structural mass is going to be easy, right? It's just multiply by zero point 0.1, which is going to be 37.0 kgs. And how about propellant mass? There is one more thing also you can do. So what you can do is, you can just subtract structural mass and the initial mass of third stage into this mi of 2 in order to get propellant, right? Yeah, anyway we are going to do that. 2037 plus how much is this? 3191.35 minus 2370 is nothing, but I'm getting some 15,141 kgs or 142 kgs. I hope you are also getting the same answers.
Could you explain the mass of propellant for stage 2?
Mass of propellant for stage
Stage
2. Okay, okay. So it is it comes from this equation. We have mi of 2 to be so the total mass at stage 2 is going to be the mass above it, which is stage three's total mass, plus the structural mass of stage 2, plus the propellant mass of stage 2, right? So what we found from here is mi of stage 2. So we can write this as mi of 3 plus, so and ms of 2 plus m propellant of 2, right? We know ms of 2 to be zero point 0.1 times mi of 2. We know mi of 2 to be 20,360. So this is known. Right? This is known. And mi of 3 also known, which we calculated before. And mi of 2 also we known. So we can calculate mi of propellant. Is that clear?
Yes, sir, understood.
Okay. So it's just our in order to quickly check whether the answer is right or wrong, what you could do is you can add these three propellant and this, okay, and then the mi of 3 is going to give you 2370 kg. That is the total mass you are going to have. So it's just coming from this rocket only. So for the stage 2, you need to add this, plus you need to add this structure, right? Then you need to add the propellant here. Then you will get mi of 3. That's all right. So let's go to third stage. Third stage, what we will do, we will do the same thing. We can do the same thing. uh, Vj ln of 1 divided by, it's not third stage, right? It's first stage, because we started from third stage, now we came to first stage. It's going to be mf of 1, right? So there is also one more equation with which you can solve, is based on this fractions, right? Maybe this, for the first stage you try with fractions, or you can try with this equation also, not a problem. What we know is alpha plus beta plus gamma, right? Do you guys know what is alpha, beta and gamma? Alpha is nothing but mass of payload or useful mass, right, divided by mass of total mass, mi, right? Similarly, beta we already know, ms by mi, right? And gamma, which we know is m propellant by mi, right? What we also know is alpha plus beta plus gamma is equal to 1, right? So your equation actually simplifies to be ln of 1 by alpha. For any stage, it's going to be alpha I beta I. The reason to use this equation is we know beta I, right? So you can easily find alpha I for any stage, and once you get alpha I, you put in these equations and you can get it easily. Okay, so you can either use this equation or you can use this equations. It's up to you. Maybe we'll stick to with whatever we started. Okay, you can try with this equation also. So mass of final at first stage is going to be mass of can you guys tell? So at the end of first stage, so this is at the end of first stage, what we are going to have, we are going to have the total mass at the second stage, right? And then we are going to have this structural mass. Okay, so maybe I will write it here. Second stage, which is the total mass above it, plus first stage, right? And what we know is mi of second stage we know, and then ms of first stage is going to be mi of first stage, right? Zero point 0.1 times mi of first stage. And let's say we will substitute in our equation, which is going to be vj times ln of mi1 divided by mf1. And then yeah, similarly you need to perform the calculations. And can anyone tell mi of 1 is going to be exponential of delta v1 divided by vj times mi of 2 is zero point 0.1 times mi of 1. How much? Sorry, I didn't get. Is that Digant? Is going to be how much it is going to be? This is going to remain same 3.8. How much is it? 3.896 times mi of 2. What we found was 2370 kg, so around 20 tons, plus zero point 0.1 times mi of 1. How much are you getting mi of 1?
Sir, I have one doubt.
Yeah, yeah,
So
sure.
here we are considering the above total mass now for the second stage. So it should be the mass of second and third stage mass, total mass.
Yeah, yeah, true. So for the second stage, the total mass is third stage, right?
Oh.
So this mi of 2, what is this mi of 2? This mi of 2
So sir,
is
for
not
first
only
stage,
this.
yeah, sir, it include this. Okay, I understand.
Come again?
Yeah, sir. So MAF2 include both the mass of second stage and third stage.
True, yeah. So this mi of 2 is not only the second stage, it's actually total stage. It
Okay,
also
sir.
includes the payload. So for second stage, the payload is third stage plus satellite, right?
Okay, sir, I understand.
So mi of 2 includes everything. So that's why we use just mi of 2. All right. So what is the results you are getting? Mi of 1. Maybe if I calculate 896, 2370.
Sir, 130015.5.
Okay, 130015.5 kgs, right? It's around 130 tons then. Okay, that is fine. Then how about structural mass? Structural mass is going to be one order less, 1.5 kgs, right? It's just multiply by zero point 0.1 with the mi of 1, you are going to get structural mass. And what is the propellant mass? Propellant mass, you can just add a structural mass with the initial mass of second stage, which is 2370, and then subtract it with the initial mass of first stage, 31.5. How much are you getting? Getting some 96.44 kgs. Is this right? Maybe we can tabulate it. So let me write it like useful, which is structure and propellant, right? And we have total mass, total. Okay, so let's just quickly fill because it gives you an overall view on how my rocket is going to be. Okay, so by the way, are you guys getting the answers what I get for first stage? Okay, I take it as a yes. uh, if we try to fill it, what is the first stage is, maybe we'll try from last stage. What is the useful mass, which is payload mass, which is going to be 500, and then structure mass is, I believe it is around some 319.1, right? Can you guys quickly tell what is this? 1 kgs. And propellant is, how much is propellant?
So propellant is 2372.2 kg.
So 2372 point.
2
Okay,
kg.
okay, 2 kg. How about for this? And so total would be 3191, right?
3191.5.
Okay. So for this it's going to be 3191, because for third stage the useful mass is second stage, total second stage, which includes satellite plus propellant plus structure of the third stage. Okay. And how about the structure of third stage?
Structure of third stage 2037, 2037.
Okay. And then propellant.
Propellant 15,142 kg. Like 15142.
For this is going to be 20370 kgs, and the structure is going to be how much? 13,000, right? 13,000.1, and propellant is going to be 96644 kg, and then total is going to be 130,015.5 kg. So one thing we need to understand from this calculation, what is the total mass of the rocket we have at the takeoff? What is the rocket total mass at the takeoff? Here, right?
Yes, sir. 1 lakh
It's going to be
tons.
130,015.5 tons or 5 kgs, okay, which is almost equal to 130 tons. So in order to put a 500 kg payload at 500 kilometer altitude, have a rocket of 130 tons. Okay, that is the uh, so and how much the propellant we are going to have? We are going to have 96,044 plus 15142 plus 2372.2, right? We are going to have some around mass of propellant we are going to use is going to be around 114158 kgs, which is around 1114 tons. So in order to put a 500 kg or 500 kilometer altitude, we have to use this much amount of propellant, and the rocket should weigh 130 tons. So there is a fun fact in this. Whatever you calculated till now is actually for a real rocket. Do you guys know what is the rocket? Which rocket weighs around 130 tons? It is in
GSLV.
GSLV. GSLV is very high. GSLV is the heaviest
Yes,
rocket.
it is. Actually, it is PSLU, right?
It is also a little bit heavy.
SLV, sir.
Not considering Excel variant, sir.
So
Uh-huh.
is it SLV?
SLV. Actually, you are close. It's the new variant of SSLV. I think day before
DPD,
yesterday
sir.
they launched, right?
Yes, yes, sir. Yes, sir.
So if you go and look at it, it is around 120 tons. It puts 500 kg satellite at 500 km altitude. That is the maximum it can put, and it weighs around 120 tons. So whatever you designed till now is actually SSLV, which is being used, the recent version of rocket. Okay. Of course, we consider few assumptions like beta to be 0.1 and delta V is equally, you know, distributed between the stages. Maybe what you can do is you can go to the website of ISRO website, and what you can see is you can get some data of peak thrust each stage can produce. Okay, Fi and the burnout time, okay, burning time of each and every stage, and with this you can find the delta V used by each and every stages, and with this also you can calculate all the propellant masses, structure masses, and the payload mass for each and every stage, because that is also going to be um, three stage. In fact, SSLV has also has one more velocity correction stage. I think it's VTM stage, velocity trim module. Including that, it is 120 tons. Whatever we modeled is also whatever we designed as a rocket is also for the 500 kg, 500 kilometer, but we are getting more mass, 130 tons. So just understand how uh, uh, cautious ISRO would be to, you know, design SSLV, and they were able to get it down by 10 tons, and they were also able to add one more module for correctioning velocity. And in fact, the delta we considered is for just 8.2 kilometers per second, but in real time it should be able to satisfy till 9 kilometers per second. If not, your the what do we say, the lifetime of the satellite comes down, because satellite also has the thrusters, and if you are not able to correctly put it in the orbit, the satellite thruster is going to take care and put it in the orbit, and once it puts in the orbit, the further corrections on the satellite throughout its lifetime is going to get reduced, because it's already spent the propellant for correcting the initial part. So the lifetime reduces, which we do not want, right? So all these things have been taken into account in order to do this SSRV. And in fact, if you go and see, it's going to be solid propellant rocket. It's going to use some fuel called APHTPP propellant, which you will learn eventually. And it is also going to have the velocity to be around 2000 meters per second only. So that's why I gave this specific example in order for you to understand few real-time situations what is happening. Okay. So do you have any questions? Yes.
Yes, sir. I have a question for the assignment 3. Hello.
Yes, yes, Digan. Please carry on.
Sir, in assignment 3, there are question asked that acceleration of the payload at the moment when the rocket is about to stop firing in meter per second square expressed to two decimal places. And the second question is takeoff acceleration of the rocket. So, the formulas discussed in the lecture is that acceleration is equal to mp into vj minus mi into g upon initial mass. So this formula for each question we have to apply this. Sir, there are formula discussed in the lecture.
Yeah.
Acceleration is equal to propellant into jet velocity minus initial mass into gravity g upon initial mass. So this formula we have used for each question. So takeoff acceleration of the rocket or the acceleration of the payload at when the firing is stopped.
So, yeah, good question. What I would suggest is, you if you go and look at how this formula arrived, you won't be able, you no need to ask this question. Let me do that also. Anyway, we are going to have this question that's going to be coming in fifth one, but I will go a little ahead. Okay. So,
Yes.
so here you have, this is the mass of the rocket. Let's say this is the rocket, and what you are going to have thrust here, right? The thrust which is giving, which is nothing but m dot into v jet, right? Vj, right? And what we have is we have a mass of gravity here, which is mass of the rocket times gravity, right? And then you apply Newton's second law. That's all. So there's no need to follow a formula. Okay, what is Newton's second law? The summation of all the forces is going to be mass times acceleration. So what are the forces you have? You have a let's say our x is like this, okay, or let's say y this direction. The ft is going to be positive and gravity is going to be negative, which is nothing but ma, and this is going to be m dot into vj times mg times divided by mu. Now you are asking what would be at the third stage, right? So you do the same calculation for the third stage. At the end of third stage, or the middle of the third stage, or after the separation of payload, before the separation of payload, whatever you do this Newton's second law for the third stage. Okay. So basically, since it is in your week 3 assignments, I'm not supposed to do that for you. You have to do it by yourself. I just give you how you can approach this problem. Is that fine?
Yes,
Yes,
sir.
sir.
So you understood how this works, right? So the thrust is going to be same. The mass of this thing is going to be same. But what should be your mass? That you should carefully find. Okay? That is something you need to be careful. And thrust is, I think, most probably it will be same. You please check it out. And this m, if you find it carefully and if you put it in this formula, or if you just do a Newton second law, you are going to get the solution. Okay.
Sir, so for third stage, we have to consider the mass of satellite only, or the structure also.
Thrust, where for thrust there is no mass of satellite or structure, right? What it says is m dot. M dot is nothing but mass flow rate of gases coming out of the rocket. It has nothing to do with payload. Payload is not coming out, right? Payload is not coming out, structure is not coming out. Propellant is only burning and it produces a lot of gas and it's going to come out of the nozzle. M dot is different and capital M is different. How do you
Sir, I
find
am
M dot?
asking for capital M.
Capital M, yeah, that you should only find out. What is the thrust is not, thrust is M dot into Vj. There is no change in M dot into Vj. But what is this capital M? You need to find out. Okay. I can't tell you the solution for that because it's in assignment of week 3. Maybe we can discuss in the next uh, lecture. Okay.
Okay, sir.
What should be my M at the end of third stage? Okay. So should it be just the payload? Should it be payload plus structure? Should it be total initial mass of the third stage? It's you need to think carefully and do it. Okay. So if there are no more questions,
Sir, so
yes,
can you
Yogesh.
explain that m dot part, like how to find the m dot?
Okay, so how do we find m dot? I will, yeah, sure. Maybe what we will do is, anyway I'm going to find the m dot in this problem also. Uh, you will get an idea how m dot is found. Okay, is that
Okay,
fine?
sir.
Okay.
Yes, sir, fine.
So second is over. We found all the masses here. Now what we will do is we'll find the total impulse provided by the rocket. What we need to find is we need to find total impulse provided by the rocket at every stage. So you know how to find the impulse. Let's do that. Total impulse. What is the formula for impulse? Force into time, right? What else we know? Is it force into time?
Can say change in momentum also.
Okay, change in momentum. How do I write it? Delta P. You can also write F into delta T, but all these things is not giving you any idea of what is the total impulse, right? What we also know is, can you guys tell me what is specific impulse? Impulse by mass of propellant, right?
Yes, sir.
Yes, sir.
So the amount of impulse produced per unit mass of propellant is what specific impulse, and you need to know that this is the most important design parameters or performance parameter of any rocket. So whenever we develop a new rocket, or whenever we develop a which is which has to be considered, the first thing they ask is what is the specific impulse, how much impulse I'm going to take, I'm going to get for burning this much of propellant is what they are going to ask, and what we are already always interested. Okay, this is the figure of rate. This is the performance parameter of any propulsion system. It's just uh, this is what always we consider. Okay, specific impulse. So uh, here, do we know specific impulse? Can you guess what is specific impulse? If you go back and check, it is nothing but exit velocity or the jet velocity. Okay, we know jet velocity, we know the mass of propellant, so we can find the specific impulse for each and every stage. So is this clear? Do you know how we got specific impulse to be jet velocity? So you need to go back to the lectures and you need to check uh, how do we get specific impulse as a to be jet velocity. If I want to quickly give you, it's nothing but F into delta V by m propellant, right? It's nothing but F is nothing but m dot into Vj times delta T by m propellant, right? M dot into delta T is nothing but m propellant by m Vj divided by m propellant, which is nothing but Vj. Okay, this is how we got this. I'm just giving you a quick overview. Please go and revisit once. But specific impulse is nothing but exit velocity, or we can say effective exit velocity, because in while doing this we made few assumptions. While doing this, while going through this process, we made few assumptions. We need to be careful about that. But now what we do is we will consider it to be jet velocity. Okay, so if we consider it to be jet velocity, specific the impulse at first stage is going to be Vj times mass of propellant at first stage. Okay. Similarly, impulse at second stage is going to be Vj times mass of propellant at the second stage. Similarly, impulse at third stage is going to be V of J into mass of propellant at the third stage. All right. So you guys can calculate this and you can check for yourself. I will move ahead with the fourth question, because this is just for you to understand few things. That's why I gave this question. Anyway, um, this is also done. Now what we have is, if the burning time is given, how do you calculate thrust? Right. So burning time given is 100, 150, and 200. TB2 is 150 and TB3 is 200 seconds. So burning time for the uh, that stage. Okay, within that 100 seconds, all the propellant will be burned. Okay, so so how do we calculate thrust? Thrust is going to be what we already know is impulse is going to be force into time, right? TB1. So I1 is going to be F1 by T1. So F1 is going to be I1 by TB1, right? and similarly F2 is going to be I2 by TV2. F3 is going to be I3 by TV3. All right. So using this, you can find the force also. So how much amount of thrust you are getting from each and every stage you can find. All right. So this is simple calculations. I hope you can easily do it. Uh, this is also done. Find the initial acceleration of the rocket at the ground. So let me come back with this. Find the initial acceleration of rocket from the. So how do you approach this one? Initial acceleration. What we do is, as I said before, for one of the students' question, this is our rocket, right? This is our rocket, and we are having some initial mass, and it is going to be attracted by the gravity, okay? And we are going to have some thrust. These are the two forces going to act on the rocket, and first we are going to neglect drag, but initial acceleration, initially there is not going to be any drag, so you can neglect that also. Just apply Newton's second law. Okay, summation of force is going to be mass of the rocket into acceleration, and F is this summation of forces is going to be positive force, which is thrust, minus mass of the rocket into gravity times mass of the m into a. Right now, this is the acceleration, F minus mg by m. Right, lot of things in this. This is what we need to use to find the acceleration. But how do we find all these things? We know gravity. Gravity at the ground would to be 9.81 meter per second square. What should be by mass? M of the rocket. Initially, what would be? We already calculated, right?
So 130 tons.
Exactly. So it's going to be 130 tons, 10 power 3 kgs. Okay. And now we need to find F, the total thrust we are going to get initially at the first stage. What we did is we found it here itself. There's no problem. Um, let's say we will find using mass flow rate. Let's say what we know is F is going to be m dot times Vj, right? Thrust is nothing but m dot times Vj. You guys know how we get this relation, right? Times.
Yes.
So this m dot times Vj. Let's use this approach. Okay. Uh, this is m dot. Nothing but mass flow rate, right? Mass flow rate of gases out of the state. Gases, which is nothing but going out of the rocket. What we know is we know burning time. Burning time at the first stage is going to be 100 seconds, right? And what we also know is mass of propellant at the first stage. So the propellant mass which is present at the first stage is going to be completely burned in 100 seconds. Then it is easy to find m dot, right? What is the mass of propellant at first stage? Uh, is it 96?
96, 96, 644
644 kgs. Very good.
kgs.
Right. Now m dot is nothing but mass flow rate of gases coming outside. So what is this gases? When the propellant burns, it converts into gases and it's going to come out. But mass is going to remain same upon combustion, right? So I'm going to burn mass of propellant at the first stage in 100 seconds. So my mass flow rate is, if I assume it to be constant, it's going to be just mass of propellant by the burning time. Okay. So it will be just 96.44 divided by burning time, which is nothing but 100 seconds, right? Then it is 6.44 966.44 kg per second. Now you substitute in the f is going to be 96.44 into jet velocity, which is 2000. How much is it coming out to be? 88 kilonewtons, right? You can write,
Yes.
okay, 19328 meganewtons. This is the amount of force you are going to give using this. And what would be the acceleration I would get? Acceleration is going to be 1.319 1.9329 into 10 power 6 minus mass of rocket is going to be 130 tons. 130 into 10 power 3 into what is the gravity is going to be 19.9181 divided by again 130 tons. How much is the acceleration you are getting?
So 5.05 meter per second.
0.05 meter per second square, right? So this is one way we calculated force to be, I mean the thrust to be m dot into Vj, right? But we also have this. We already calculated this. Let's calculate this. How much is the F1 you are getting? Now for that we need to know I1, right? How much is I1 you are getting? Vj times m of propellant. What is Vj? Vj is 2000.
Yes, sir. The answer is 1932.
Oh, F1. Is it F1?
No,
1932.
sir, I won. I'm taking I won.
Okay. How much is that? 1932
Double 8 kilonewtons.
8 kilonewtons. Okay.
Yes, sir.
Now you do the
Then,
same thing. 193288 divided by burning time. How much is burning time? 100 seconds, right?
sir.
How much you are getting?
32.88
1932.88
kilometers.
kilonewtons,
Kilonewton.
which is equal to 1.32. Uh, you see, this and this are same, okay? Because it's actually coming from the same formula. You just calculated impulse and then found the force. What we did was we calculated from the mass flow rate and then we found the uh, thrust. So both are actually same equations. It's just written in different forms, and it should give you same solution. So is that fine? How do you find the mass flow rate of gases? I think someone asked. Yogesh, is that Yogesh who asked?
It's fine, sir. No way.
So you understood, right? How this
Yes, sir.
happens? Okay.
Sir, what if we can do like if they ask the question like what is the thrust produced by a rocket? Do we want to add that thrust, each thrust produced by each state, each stage?
Answer it. What do you think?
I think I will add the thrust provided by each stage. I will add everything and then put.
Yeah. So ultimately, at the end, how much thrust your thrust is going to be dictated by each and every. So at first stage, I'm going to produce some 1.3, 1.93 meganewton. The second stage, I'm going to get some maybe some zero point 0.2 meganewtons. I have some answers. So and then at the third stage, I'm going to get some 20 meganewtons. But the total thrust is going to be just addition of all these things. Only thing is we divide it into different stages and we are allowing it to burn at different rates, right? So that we will get different thrust at different intervals of time. That's all. But the total thrust for this rocket, total thrust required to put a 100 kilometer altitude is going to be addition of all three stages thrust. True.
Okay, sir. Thank you.
All right. Do you have any more questions? So let me check the question first. Okay. So we finally found the initial acceleration too. And one more question you might also end up getting in your uh, assignments is so week 3, right? So you might end up getting what would be the acceleration at the end of third stage, right? Uh,
Yes, sir.
so all those
Sir,
things, yeah.
in assignment, I have one doubt. Like in the second question, they're asking about the kinetic energy of projectiles. Can we have
Which
any
which one?
second?
Assignment 3,
Yes, sir. As in week three.
week 3 assignment, second question.
Second question, question number 14, like the second
Okay.
topic, question number
Kinetic.
14. And do we have any examples like this for that?
Okay, what has been asked is that there is a different satellite of mass 400 kg as orbit of 8 kilometers per second. It shoots a projectile of mass 40 kg with a velocity 2 kilometers per second along the direction of its motion in the orbit. Okay. Um, Determine the following and suitably fill in the examples. Fill in the blanks for question number 16. So there is this 400 kg mass, the orbital velocity 8 kilometers per second. So 2 kilometers per second. Initial momentum of a satellite before firing the object. Okay, final velocity of satellite when projectile leaves. Okay, velocity of projectile as it leaves the satellite in the initial frame. Kinetic energy of a particle received by the observer in initial frame of reference. Okay. This is interesting. So actually, I didn't frame anything. It's just I'm also new to this question. So there is this some satellite which is in orbit. Okay. And what we know is it is moving at velocity some 8 kilometers per second, and it has a mass of 40 kg. And as it goes, it is going to shoot some. Wait, is it mass of? It's 400 kg, right? It has 400 kg. When it is going, it is going to shoot up some 40 kg mass with okay. They're asking series of questions. Kinetic energy of particle in kilojoules as perceived by an observer in the inertial frame of reference. Okay, so you need to think when you talk about kinetic energy. What is kinetic energy? mv square, right? And they are asking for a projectile, right? Which is this thing, 30 kg, which is released at 2 kilometer per second. And the catch here is, what is the mass here? Is it 40 kg or 400 kg? Uh, is the velocity here? It is 2 kilometer per second or 8 kilometer per second. Something that you need to think. Yeah, this is interesting. So my answer is it is asked in inertial frame of reference. So express all the velocities in inertial frame of reference, and you try this equation. So that would be my hint in order for you to understand. uh, I cannot tell you how to calculate because it's your week 3 assignment, right? Maybe we will discuss in the next lecture.
Yes,
Okay.
sir.
Okay, so you understood, right? What I'm trying to tell.
Initial
So
frame, I need
it's
to
inertial
take.
frame. So express all your quantities in inertial frame, and then find the kinetic energy.
Okay.
So yeah, express it in inertial frame. You know what is inertial frame, right? It's either
Mm,
moving at constant velocity or it is moving in uh, uh, either it is stationary or moving with constant velocity. So yeah,
It's moving with constant velocity. I am the viewer, I am in a stationary position.
So it is asked for inertial frame of reference in kilometer per second. Okay. Yeah. So try doing it. Let's see. By an observer in inertial frame of reference. So observer is not in satellite, right? Mostly, you won't be in satellite.
We take the Earth stations as observer. We have stations, Earth stations to have connection with satellites.
Right. So, uh, so inertial frame is just something. It is stationary. Okay, think it like that, and then you try to um the velocities, express velocities in inertial frame for both mass and satellite, and then for whichever kinetic energy they are asking, you just put half mv square. Most probably, yeah. Give it a thought. Let's see. We'll discuss in next class. Other questions, I think all others you should be able to answer, right? So I covered everything in one. I tried to cover everything in this one question here. Okay. Only thing is, here they gave all the stages, propellant, structural, and jet velocities also, everything separately. What we did was we took some mass ratio, and they were asking ratios, right? In the assignments, what we did was we did opposite. We took a ratio and payload, and based on that, we try to find out the propellant mass, structural mass. That's all. Other than that, every equations and applicability of equations going to be same, and I hope it will be easy for you to answer this assignment. There is a few questions like catapult launcher also.
Yes, sir.
I am not going to discuss this. We will discuss in the next class. It is for you to think and provide the answer. It's interesting. So if not, if you don't go with the rocket, there are few catapult launches also. You can search for it in the Google. Instead of using a rocket to launch a spacecraft, you can launch using from the ground. You can just throw it away. And if you're trying to throw it away, what are the changes it's going to have is what they have been asking. And I will leave it to you to think and answer. We will discuss in the next lecture. Okay, next session. So other than that, do you have any more questions in either this week's assignment or this today's question or previous week's assignment or even lecture videos? Suggestion for you guys is to go and look at this SSLV, okay, and look at its specifications and try to find what would be the thrust or what would be the given by each stage, what will be thrust given by each stage, and what would be, so they would have told that the total mass is going to be 120 tons, but they wouldn't have told that what is the mass of each and every stage, right? So you can try to understand those things by doing these few calculations. And you can also there is this propellant they are using. They are going to use the same propellant for three stages, and for that propellant the velocity is almost same only 2000 uh, meter per second. Actually, it's around 2500 meter per second. It has a specific impulse of 260 seconds, the APHTPB propellants. So the jet velocity will be around 2500 seconds, and using these and maybe beta also, you can find what would be the beta they would be having, what is the state of art they are having at a zero. So all these things you
So,
can find and find.
so I have one doubt in last lecture, that is lecture 9. And lecture 9 in the last few seconds, he has derived the formula of F flex velocity, wrong, sir? which is equal to Vj equal to square root of 2 or
Yeah.
yes, sir. In that, what is the gamma signifies, sir? Because he said only gamma, gamma, but he haven't said what is the gamma.
So
Because it has
you're referring to this one, like Vj is square root of
2 or uh, 2 gamma, sorry, sir, 2 gamma. First 2 gamma, 2 gamma.
Pc by molecular weight, I guess, and
No, sir. He did it like 2 gamma R naught Tc, like universal gas constant.
yeah, R naught Tc,
Tc by gamma minus 1 into molecular mass.
P by Pc, right,
Yes, sir.
into gamma minus,
1 by gamma.
right?
Yes.
So actually, this gamma is nothing but Cp by Cv, which you know, right? But thing is, so the one important thing to note in this equation is that when you increase Tc, you are going to have Vj to be more, right? That you understood, right? When you decrease the molecular weight, again you are going to have Vj to be more, and when Pc by
Yes.
P is going to be less, again Vj to be more. These three things you understood, right?
Yes, sir.
So uh, now, what is the effect of gamma? So in this equation, we addressed molecular weight, we address Pe by Pc ratio, and we address Tc. R naught is, of course, is universal constant, but there is this gamma also, right? So what
Yes,
is
sir.
the effect of gamma? That is what is been. I hope that is what it's been addressed in the lecture. So usually, if you say for gamma is equal to 1.6 for monoatomic gas, okay, 1.4 for diatomic gas or others, gamma 1.3 or 1.1 around that for polyatomic gas. So if you see, the gamma is not varying that much, it is not varying with orders of magnitude, just 1.1 to 1.6. So this gamma is not going to affect much of your Vj, but if you want to see what is the effect, if you increase gamma, what happens is it has reached monatomic, right? Which means the molecular weight of a monatomic gas is very less, right? So if you increase gamma, the Vj should decrease, because if you see the effective contribution of gamma, Vj should decrease. But since molecular weight decreased, the Vj will increase. So it's actually one parameter is trying to decrease the velocity, but other parameters will increase the velocity. But the net effect, what happens is this increase in velocity is dominated. So the effect of gamma in the Vj is very less, but the effect of molecular weight in the Vj is very high. So if the molecular weight is decreasing, the Vj is going to increase. But when the molecular weight decreases, gamma is going to increase. But because of gamma increasing, Vj should be less. But that less is very less compared to the increase in Vj due to molecular weight. That's why overall, when the molecular weight is decreased, or when you go to monoatomic gases, uh, we are going to have very high exit velocity. That is what is being tried to portray in the lecture. Is that clear now?
So it's clear now.
Okay. So
So
the
gamma has no role to play in the inject velocity. It has
yeah,
very
it has
small
very
role.
minimal effect, but it is overtaken by other parameters in the equation. So it has almost negligible role to play in, yeah, true. That is true. So maybe I can give you a little bit interesting fact here. Okay. So if you look at this, in rocket, what you are trying to do. So what is the major energy conversion processes happening in rockets? So we have propellant, right?
Yes, sir.
We have propellants here, and then we have a nozzle here. Okay, so you will learn more about nozzle, but simple energy conversions, if you want to see, this propellant is has high chemical energy within it, right? What
Okay.
you're trying to do is you're trying to convert this chemical energy. Okay, so upon combustion, what happens? The gases temperature rises, right?
Yes, sir.
If the propellant
Yeah.
is a propellant has a high chemical energy, let's take a fuel, let's say petrol or diesel. What they have is upon combustion it creates very high energy. In your CI engines or SI engines, it going to, in addition to high energy, it's going to produce high pressure also, which pushes the piston down, right? That is what happening here. There is no such piston arrangement. What happens is just rises the temperature to very high. So what you are doing, you are having very high temperature, and this high temperature, what actually happens is it gets converted into kinetic energy. Where it gets converted is this nozzle. This nozzle, what it does is it converts a thermal energy into a kinetic energy. Okay, kinetic energy gives to very high velocity. So let's say for a nozzle, if you see a nozzle at the inlet, if I have more thermal energy, I'm going to have more kinetic energy at the exit. Okay, so if I need more thermal energy, my temperature inside this combustion chamber should be high. So if I have more thermal energy, I am going to have more velocity at the exit. So that is based on logical conclusions. You can come up with this. Come up with this. Is that clear? Based on just simply logic, you can apply logic. This thing. If you rigorously derive also, when you rigorously derive, you will know what is sort of dependence. So Vj is actually uh, uh, proportional to square root of Tc. That we don't know using logic, but based on this energy conversion process, we can say if I have high thermal energy at the inlet of nozzle, I'm going to have high kinetic energy at the exit of the nozzle, which you will see in subsequent lectures or subsequent assignments also. When you increase the gas temperature, you're going to have high velocity. And second one is molecular weight, right? What does this molecular weight plays role? So nozzle is nothing but an accelerator. Okay, you see nozzle as an accelerator. It accelerates the gases to very high velocity. Initially it will come at very low velocity. In the nozzle it gets accelerated to a very high velocity, supersonic velocities, or yeah. Here, if you have a very high molecular weight, the mass of the gas is very high, what you are going to have is it is not easy for nozzle to accelerate. It's going to be, it has to give more force in order to accelerate the very heavy propellant or very heavy gases. Okay, if I have a very hydrogen gas which is very light, it is easy to accelerate. Okay, so that's where when the molecular weight of when it decreases, the acceleration inside a nozzle it's going to be easy. It's the nozzle is going to easily accelerate because mass is less, so you can easily accelerate the gases. Okay, um, another thing is pressure, which again you will see in the nozzle. At the inlet, if I have high pressure and the exit I have low pressure. Okay, PE is nothing but exit and PC is the inlet pressure for the nozzle. I'm talking about nozzle. PC is the combustion chamber pressure, which is the inlet pressure for the nozzle, right? So if I increase the pressure, from fluid mechanics we know that the flow is going to happen. If I have greater pressure gradient, I'm going to have very high flow. If I have less pressure gradient, I'm going to have a very slow flow. Okay, so that is the logic you will apply. So when there is an increase in chamber pressure and exit pressure is going to be same, or the ratio of this is going to be small, or you can write PC by PE is very large. Okay, chamber pressure is very high than PE, then what happens, a very high pressure gradient is imposed, which is accelerating the flow in the nozzle. Okay, so that is what happening in this that is what, if you logically think, you will be able to arrive at this results. In order to get accurate proportionality between these parameters, you have derived a state, you have imposed a steady flow energy equation, assumed a lot of assumptions like calorific gas, isentropic process, and adiabatic walls, and all these things you assumed, and then you arrived at that expression, which gives you more correct dependence. That's all. But logically also you can think about this. Okay, is that making sense?
Yes, sir. It's clear.
Okay. Do you have any more questions?
So it's everything's clear for me.
So we have a few more people: Purvi, Sagar, Sandra, Muhammad. So I hope everything is clear for you guys also. Please feel free to unmute yourself and ask me questions at any point of time. Um, I think it's 9:05. Maybe I will stop here and we will meet next week.
Thank you, sir.
Yeah, thank you.
Thank you, sir. Have
Thank
a
you.
good week.